We had to do something. So if you put a greeting in the chat, remember that little button down at the bottom, make sure it says panelists and attendees. It defaults to just panelists. And I think that more than just me, Vivian, Dave, and Kathleen would like to see what you have to say.
Yeah. Nice.
And Vivian, you did it.
I just put it in there while you were talking.
You sent it to panelists only.
Yeah. Oh. Oh, man. Fooled. Let's try that again.
So what do you guys think about the water on the moon's discovery? Is it just an increment forward, or do you really think it's something new and big? Let me know. I would like to know. They ask me about these things in hi Daniela. They ask me about these things here all the time, and some people here are divided. They're like, oh, it's just the same old, and others are like, no, it's a brand new thing. It's really great. So what do you think about water?
No, I haven't read it yet. So.
Oh, got to read it. Read it for me and let me know.
Every time NASA says we have a big announcement, everybody's like, oh, we found him. I think it's going to be a letdown every time. I think it's very cool, but it's not aliens.
Good answer. I'll be on the radio about it here for like 15 minutes, and that's a long time on radio or TV. So I want to use it to talk more about exploration of the solar system, because people here are really interested. We have a space agency here now. We have Rocket Lab, which is really successful, and Rocket Lab wants to get out of low Earth orbit and delivering satellites and wants to go to the moon and Venus. So I think they're going to do it. So New Zealand is right on the map, and so people want to know and they ask, and I'm excited. But then when you find out how hard it is to get the water out of the dirt that's on the moon and stuff like that, it's like, ooh, there's more work to do here.
Yeah. I remember when I heard the announcement, we found something. I assumed it's like, did they like just find a water molecule where they weren't expecting it? And then it's like, kind of, yeah. It's like what in like a meter of soil would have X amount of water, like
a liter or something. And the other thing was that they had found hydration, evidence for hydration, but they couldn't tell whether it was hydroxyl, which is OH, versus H2O. And now they know for sure it's in the H2O form, which was great. But I thought, well, does that make it easier to turn it into stuff you can drink or rocket fuel? And I haven't found the answer yet to that. I'm looking through the internet looking for that. So we'll see. Mm-hmm. Mm-hmm. But it's gateway.
Yeah, exactly.
With Mars. So that's the interesting thing. And starting to spend more time and in cislunar orbit or thereabouts is all really interesting. And I've been, dying and waiting for the James Webb telescope to be launched. And that's going to be it. I forget what the name of it is. You guys probably know. There's one side of the moon is called one thing, and the other side, they're going to stick it in one of those Lagrange points on the other side.
Yeah. Like,
so I'm keen on that. Yeah.
Well, we're at the top of the hour, and so let's get started. It looks like we're getting a good crowd here. And just another quick little reminder, and actually let me hit the record button before I forget. I'm sure to forget if I don't do this now. So just a quick little reminder, please make sure on that chat window that you go down to the bottom and select panelists and attendees. And so we had people trained earlier, but then we had a whole lot of people show up after we had that announcement. So hello, everyone, and welcome to the October NASA Night Sky Network webinar. We're hosting tonight's webinar, as usual, from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to present this webinar with our guest speaker, Dr. Kathleen Campbell from the University of Auckland in New Zealand, where it's tomorrow. And we also have with us Daniela Scalise from the NASA Astrobiology Institute. And so Daniela might have a chance to say hello here at some point as well. Welcome to everyone joining us on YouTube live stream. We're very happy to have you with us. These webinars are for members of the NASA Night Sky Network, though we look forward to seeing everyone else on YouTube. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, I'll see if I can convince either Dave or Vivian to pop a link into the chat so that you can follow it and learn a little bit more about what we're doing. Before we introduce Dr. Campbell, here's David Prosper with just a couple of announcements. Dave?
Okay. Hi there. And in case I type anything into the chat by accident, it's because of this beautiful gentleman here who was walking on my keyboard. But yes, what do we have for announcements? A couple of things. They're very fresh, so I don't have links for anyone yet. These will be in our newsletter coming out in the second week of November. First of all, NASA is looking for folks that want to host watch parties for the Perseverance landing on Mars this February 18th. So when we have more information, that'll be put into the newsletter and distributed out to all of our members, and you'll undoubtedly hear more about that opportunity soon. And in more news, we of course have the annual award pins, and the design is almost ready. So with luck, we'll be able to start the order process for folks in probably late November and early December, maybe a little earlier, maybe a little later, depends on how logistics work out. As we all know, it's a little funky. So we made a few tweaks to the pin designs and program itself based on your feedback, and we're really excited about these very excellent changes. But since it's all not quite done yet, you're gonna have to wait for that announcement. Also in the newsletter in the second week of November. But I do have a little hint about the design. Just that there was a pretty nice surprise for stargazers earlier this year, and that may be a factor. And that's what I got for y'all. Back to you, Vine.
All right. Thanks, Dave. Now I'm really curious. I haven't even seen the pin. I have no idea what's on it. And so now I'm really curious.
Okay, we got just 2 folks so far and the designers. That's 3.
Okay. All right. So for those of you on Zoom, you can find the chat window and the Q&A window at the bottom edge of the Zoom window on your desktop. Please feel free to greet each other as you've been doing in the chat window and making comments about our various costumes tonight. So thank you for that. And also to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. If you have a question for our speaker this evening, please type it into the Q&A window. It really helps us keep track of them and lets us know if we've answered your question or not. So please put those in there and not the chat window. And so we'll put a couple of reminders about questions to go in the Q&A window. So again, we want to welcome everyone to the October member webinar for the NASA Night Sky Network. This month, we welcome Dr. Kathleen Campbell to our webinar. Professor Kathy Campbell is a geologist and an astrobiologist who investigates extreme environments as analogs for early life on Earth and possible life on Mars. She studied at UCSC, the University of Washington, USC, and NASA Ames Research Center before joining the University of Auckland in New Zealand. In NASA's Mars 2020 landing site selection, her team's proposal was one of the final 3 with the aim to collect samples possible Martian biosignatures from over 3 billion-year-old hot spring deposits in the Columbia Hills and Gusev Crater, which were, and also to revisit the Spirit rover and see whether or not it's been buried yet, I'm sure, and their eventual return to Earth in a future mission. So please welcome Dr. Kathleen Campbell.
Yay, thank you so much. Nice introduction, Brian. Thank you. It's great to be here. It's in the afternoon in New Zealand tomorrow, but let's not think about that too much because it gets a bit confusing. But I'm here. Yes, I'm native Californian. I was born in the Bay Area, and I studied, as you could see, overseas where you are, and then moved in 1997 to New Zealand, where I have been teaching at the university. So I'm really looking forward to this talk tonight for you. And I'm just going to share my screen here and pop this up and see if everybody's happy with this. Brian, you guys can see okay? I think you can.
Yep,
looks great.
Thanks, guys. Just double checking because we've already had a check on that. Well, you know, I know, I'm sure you've thought about this question, like almost any person on the planet, that this idea of are we alone? And I thought we might talk this evening about this idea of searching for extraterrestrial life in the solar system. So much is going on, in fact, in this space that I just taught an astrobiology course this semester. We're just finishing our second semester. So our year finishes in December. We have a calendar year and we finish in December, not mid-year. And we just finished talking about all these topics in my course, Astrobiology, which is across my university. It's got philosophers and students who study Korean and engineering and every possible discipline. And it's been really exciting. So I want to, and every week we had new discoveries, of which we'll talk about a few of them here this evening. So there's some night sky in the southern hemisphere here over the Southern Alps, which are in the South Island. And that's a very beautiful photo taken by some professional photographers here in New Zealand, which they allow us to use these photos, and they're fantastic. So the other thing I just point out is that I'm the director of a Center for Fundamental Inquiry known as Te Ao Mārama, which in Maori means coming into the light. And it's in regards to the whakapapa, or the genealogy of creation that Maori believe, as well as it also alludes to the first light that a telescope sees. And we've got a research center here that we have people in computer science, physics, geology, chemistry, the business school, a whole bunch of different people involved with this group. And it's been pretty exciting because our space program is taking off here in New Zealand, literally. And we're really excited to be a part of the foundation of that. We haven't had a NASA as long as you have, but we've got something that is up and coming. So I'm excited about that being here. Now, so I want to talk a little bit about what's going on in the solar system in terms of searching for life. And most of you probably know what astrobiology is, but I thought I'd just have a brief reminder that in a way, it's kind of about everything, in the sense that it's the story of life in the universe and into the sort of fundamental questions about, who we are and where we come from. And it has three parts. It's basically everything to do with the origin, the prebiotic chemistry of different planets or worlds, the origin of life itself and its evolution, and that's sort of one part. And then another part is searching for life beyond Earth, which will be a fair amount of our conversation this evening, in terms of habitability and where you might look for life. You just don't go out and randomly look around. And then considering the future of life on Earth and elsewhere. And I think you've already realized that we use tools from almost every discipline, including philosophy, social sciences, and all the sciences and engineering. So it is very exciting, and we have to try to learn to communicate with each other across these disciplines, and that's something that my group's quite keen on here. So we're very, very happy I'll be very happy to highlight a few things about searching for life here in the solar system. But let's step back just for a moment and remember that we're asking these really big questions about, are we alone in the universe? And the latest estimate I've seen is if you count the galaxies that we can't see, but how we can estimate those galaxies, it's something like 2 trillion galaxies in the universe. And a question about how many might have Earth-like planets, back when the Drake equation was postulated by Frank Drake in 1961, they didn't really know the answer to that question. And we're getting closer and closer, of course, to being able to answer that question now with extrasolar planets. So this is a spectacular vision through the Hubble Extreme Deep Field campaign, and just looking in one tiny, teeny portion of what looks like blank sky, and this is what you see when you look for a while. So I'm really a keen proponent of observation, and we're going to be looking at some of the work that we do in the earth sciences area around supporting our search for the origin and earliest life on Earth, as well as the possibility in particular for life on Mars. But I'll also refer to some other places in the solar system and why we search the way we do, what we're actually looking for. So another really big question here, and we use Earth as our model, of course, is how did life originate and what was early life on Earth like? And some of you will be familiar with this giant mural in the Smithsonian painting of what early life might have looked like back in the Archean eon, something like 4 billion or 3.5 billion years ago. And you can see the volcanoes. And here we have these little mound-like things in a hot spring. This is basically what I study here in the foreground, but also these little mound-like things growing out in the shoreline area. And those are known as stromatolites. They're layers of sediment and microbes, and they are the holy grail. If we find anything like that on Mars, I'm not even sure we have to bring a sample back to prove it, but we can discuss that afterwards if you like. Now, 900 million years ago, which seems like a long time to us, really isn't so very long in the history of the Earth. And these are some fossils described from Australia that are 900 million years old, and nobody has any qualms about saying that's life, that's fossil life. But when you want to go back to billion, 2 billion, 3 billion, 3.5 billion years old, that's where everything gets a bit controversial at times. And in fact, in New Zealand, we would say everybody has a big bun fight, which just means they all start to argue about whether or not they're, when somebody says we've got the oldest life, usually there's a whole bunch of other people who say, well, hang on a minute. And then there's a lot of debate. And that's really important, because if we've got this problem on Earth, imagine what it's like when you see something on Mars, for example, with a rover, and you've got the instruments on a rover, and you're trying to prove that you've got something like this, which is on the scale of microns, and a micron is 1 × 10⁻⁶ meters, then you can imagine why people are now really starting to get serious about sample return. So we'll come back to that a little later. And of course, we want to know if there was any life on other planets, where would you look for it? Let's not just look everywhere. We need to have some sort of constraint around that, around maybe habitability, maybe around some other questions, and then make sure, that we have some ideas of what it might look like, because we don't want to step over it and step across it and not even realize that we might have discovered it. So I think we all know that we haven't found any signs so far of intelligent life from space. There have been no visits yet that we know of, either through the radio or any other way that we know of for sure. So a question that then comes to mind is, well, what about microbial life? And that's an area of huge exploration. We've got life on Earth just about everywhere we look. And the environments are even in the most extreme environments. So very hot, very cold, very salty, very deep, and sort of just about everywhere we look, we find it. And so this is just one example here of some purple sulfur bacteria. They are purple colored, and they eat carbon dioxide and they eat hydrogen. So that's around, and they give off, you see these bubbles of methane gas, and they live in a salty pond where nothing else can live, which is why they haven't been eaten. And that's, for us, that's really strange life. I know that's anthropocentric of us, but that is, we do think and feel that that's, rather extreme. And so we use, to try to understand what was going on in the early Earth back when there was no oxygen in the atmosphere, back when the volcanoes and the lavas were hotter, the sun was weaker, we try to use what we call Earth analog environments or extreme environments to try to get an idea of where life might have originated or where we might find it somewhere else. And so these are across a bunch of different kinds of environments, and some of the ones illustrated here are hydrothermal vents in the deep sea, living inside of rocks in the dry valleys of Antarctica, where there's really not much rain or anything else for them to eat in the rocks. And here, the largest hot spring in Yellowstone National Park with a walkway, and tiny little dots are people, just to give you a scale. And most of the colors you see there are different microbes adapted to different environmental conditions or extremes out away from the source of the hot spring vent. So we work a lot on these things, and people are certainly very actively searching for microbial life throughout the solar system, and perhaps, of course, beyond. Now, in terms of the temperature extremes of life, which is something we can measure relatively easily, we're up to about 121, 122 degrees Celsius so far in hydrothermal vents in terms of life being able to survive and thrive, and close to that temperature even on land in hot springs. And we do all this because we want to try to imagine, where we might find life elsewhere. So out beyond Earth, for us anyway, it's pretty extreme in terms of the conditions, but microbes and even some eukaryotes like tardigrades, which are very strange looking little water bears, those can survive some time in space. So we are looking at these extreme environments and extreme organisms and their settings to help us narrow the search for life elsewhere. And so when we talk about hot water in particular, or hydrothermal environments and the origin of life, we can find these little pink stringy things are from Yellowstone, microbes in a hot spring on land or in the deep sea here, which is where the record holder is for the hottest temperature of anything alive so far. We can look at the tree of life, and this is one of many versions of it, and go down to its deepest roots. Here are the 3 domains of life: bacteria, eukaryotes, archaea. These ones on the bottom here are all single-celled, and then here in a eukarya, we're way up here in this corner. But But if we go down to the most primitive living things, we find that those branches are purple. And in this chart, purple means heat-loving or hyperthermophilic microbes. And so there's an idea that the deepest roots, and maybe even Luca, the last universal common ancestor, maybe that, whatever that was also hydrothermal. And maybe, just maybe, that's some kind of reflection or remnant on the early bombardment of the solar system when the solar system was full of rubbish and debris left over from formation of the planets, lots and lots of impacts. And so we had that heavy bombardment period. And maybe life arose under high temperature conditions early in the history, and it's reflected in our most primitive living things. So that has been a hypothesis that people have been quite excited about for a very long time. However, new genetic work shows that that hypothesis or that idea has been questioned because it turns out that the heat-loving bacteria have got up to 24% of their genes from the archaea. So here are the bacteria over here, here's the archaea, and there's been some horizontal gene transfer. So if you look at vertical evolution, as you know, Darwin's evolution, but there's also this horizontal gene transfer. So it's now a little bit up in the air whether Luca was a thermophile. And that's a very active area of research. Now, I did want to point out, being a geologist and a paleontologist, that in fact, there are fossils, real fossils that people think are legitimate way back in what we call the Archean eon, which is, between about 4 billion years ago and about 2.5 billion years ago. And life definitely took hold somewhere in that window, in the older part of that window. And so we're quite interested in how did life evolve on Earth? Will it tell us something about life elsewhere? So these are just a couple of examples of some rocks. These from Western Australia, and these from South Africa, where we have bits of super old continental crust that preserve really old rocks. In North America, we have them up in Michigan and the Canadian Shield, and also here in South Africa and Western Australia. So here we have some filaments in a deep sea hydrothermal vent fossil, and this is a fossil biofilm, the gooey stuff that microbes exude into the environment. And so biofilm is a product also of, this has been turned to stone through silica mineralization, and now it's quartz mineral. And so these are real bona fide examples of fossils, as not quite as old as we know, but pretty far back. And things older than this start being rather controversial. So this is where we come in. Ever since my postdoc at NASA Ames back in the 90s, in the mid 90s, I was introduced to hot springs in particular by the team at NASA Ames in the Extrabiology branch. I had already been working on extreme environments that I started working on by accident as a graduate student in Western USA. I was working on undersea cold springs, basically. And so they invited me to come out and study microbes and how they get preserved in stone through time. And when I moved to New Zealand, nobody was really doing this kind of work. So we started working here, and then we expanded our studies into Argentina, where I would have been this December if I could have been. We were planning to do more work out here in December as a stepping stone into deeper time. So millions and billions of years, we go further back trying to understand the preservation of biosignatures and how that might look on another celestial body as well. But next week, here in New Zealand, I will be going to this site here, Whangapa'oa Spring, to do some filming and other sampling. So at least I can get out in the field, which I very much appreciate. So we work on these younger hot springs as analogs for early life on Earth and possible life on Mars, trying to understand how they turn to stone, basically, and using geological time and the age of these deposits, these different ages, like a movie, almost like a snapshot as we go back in time, trying to understand their preservation potential. Because most of you might recognize this as a spring, but most of you probably wouldn't recognize this as a spring. This is 150 million years old in Patagonia. So here's probably my favorite place, Orake Caraco. I'm also going there next week, a stunning location. This is a fault scarp. For those of you who are not geologists, there's a fault here that's offset these rocks. There's some steam here coming out, hot steam, and these are some hot springs down here. And all these different colors are the microbial mats that are growing. In summertime, they grow all over the place here. And the white material is silica. It's a mineral that comes out of the hot springs. It's dissolved in the springs. And the key to preservation of biosignatures is how rapidly you mineralize those microbes. And it'll be the same on Mars in the hydrothermal environments and deposits on Mars. It'll be the same on early Earth, where we're trying to understand how life took hold. So we're looking at extremophiles, extreme environment-loving organisms, microorganisms, and their rapid mineralization in what we call opaline silica, which is amorphous. It's not crystalline like quartz. And that's going to be important in a few minutes when I talk about Mars. So an example of our marching through time of some of the work that we've done is we might go to the edge of that beautiful orangey pool, and we might look down into that pool, and what do we see in there but living stromatolites? So microbial mats that are growing upwards up to the air-water interface, and then growing along the edge. The mats are growing in the summertime, they grow along the edge. And where it's drying out, where it's white, you can see that silica. So they're turning to stone right in front of our very eyes. So I had a student a few years ago grow these things with a weather station and slides every hour, every week, every month. And she showed very clearly that these features known as stromatolites, which are layered buildups of the mats, which shown here with this type of microscopy is shown in green, it's false color, and that's where the carbon is. And then the orange here is quartz or silica, and this one is 150 million years old in the lower left corner, and this one's forming last week. You can see the microbes, and then a film, a biofilm known as exopolymeric substance, or EPS. This becomes silicified and makes a very smooth silica material, but it's actually biological in origin. So this entire deposit can be tens of meters thick or more, like at Yellowstone, where the hot spring deposits become very, very thick. And almost all of it is made out of silicified or silica infused life. And this is very important for looking for life elsewhere. The question is, can these features form in the absence of life? Can this form, this feature, in the absence of life? Because the textures, if we saw this on Mars, we'd be very suspicious and say, this looks really promising. It's a potential biosignature. But the question that is still unanswered, which has to be done in a laboratory, is, can you grow stromatolites abiogenically? And the answer is without life. And the answer is maybe yes. So we have to be very careful when we're searching for biosignatures. It costs a lot of money to go into space. And we want to be sure when we find something and bring it back that we think it's a pretty good candidate for a biosignature. So these are really spectacular, really beautiful. So here we've got the modern hot spring, and then this one is just 60 years old. And you can see here filaments growing, and this is a rock thin section through a microscope. And you can see that it still has its pigments. So all these colors are its sunscreen. So these turn orange in the summer because they have carotenoid pigments, which is the same thing that's in carrots, carotene, that is like a sunscreen, a natural sunscreen. And this 60-year-old hot spring deposit made out of silica entombs the microbes in life position, and you can still see their pigments. And then you can step back in time, and this one's 150 million years old. We have special microscopy here on the right that tells us where the carbon is, which is shown here in green, and the rest is all turned to quartz. So we go from opal to quartz in 150 million years or less. And if you want to really step into deep time, this is our recent work. We've drilled the Western Australia out in the Pilbara last year, thankfully not this year, with one of my students. And we've been looking very carefully at some of these layers, and we're finding very similar textures. When you are talking about 3.5 billion year old rocks, even though something might look very much like a microbial mat, I can tell you that most of the scientific community wouldn't believe that this was a microbial mat. So there's heaps of other work we have to do to try to characterize this. And why am I going through all of this? Well, 3.5 billion years old starts to put us into the time frame of when Mars had water and volcanoes. And water and volcanoes, certainly in New Zealand, make hot springs. So you need environments, habitable environments, if you want to be looking for life and not just driving around a bunch of volcanic plains and wondering why you aren't finding anything. So the fact that we've got now preserved possible microbes 3.5 billion years old on Earth at the same time that Mars was, and in anoxic conditions, etc., similar to Mars, then you're really starting to get close to the idea that maybe life could have originated on Mars as well. So we use this stepping stone technique to go into the deep time geological record. So that's what we do in my little neck of the woods. So the drilling campaign found Very important things like when you have a vent area in a hot spring, it forms a very funny little bubbly type of silica known as geyserite because it comes from geyserine. And so here's a very recent example in New Zealand. And here's the 3.5 billion year old example from Western Australia. So telling us that life might have been on land and life was forming in hot water at this time. So we're working on that drill core now, and it's been pretty exciting, even though it's been a little bit hard. We can send samples anywhere we want, we just can't send people. Now, you may have heard about this hypothesis because you might have had Bruce Damer come talk to you a little while ago about the hot spring origin of life. And so I won't spend a lot of time on it, but the idea is this, that you can get organics raining down from space, the Murchison meteorite, for example, or interplanetary dust particles that are full of carbon. And that carbon isn't alive, it's just a building block for life. And then you have some stuff going on, at least on land here, that's pre-life, where there's prebiotic chemistry going on. You accumulate and concentrate those materials that you need, phosphorus, sulfur, etc. And then somewhere in all of this, protocells will form, and you actually then create early life, somewhere in this cascade of hot water moving down through the landscape. And, they say that Darwin in 1871 imagined some sort of warm little pond. He didn't say hot spring, but one could stretch the imagination. And then you get diversification, distribution, adaptation, and finally colonization of the shoreline of the sea, which is the extreme environment of that time, because you aren't able to concentrate those nutrients in the vast, big, huge ocean. So the place where you can concentrate the nutrients and dry things out and then form a protocell boundary is actually possibly on the land, not in the sea. So here's the old idea, the origin of life going from the sea to the land. And that's been the idea, obviously, forever. And so I'm part of the team that is exploring this idea that maybe life originated on the land and then went to the sea. And of course, we would have walked out of the sea when vertebrates came back on the land about 350 million years ago. So land to sea and then back to land again. So that's what we've been working on with a bunch of different people. So now when you take these things that we've learned about Earth and early life, which is ongoing and lots of debate, then you want to go out and explore the solar system for life elsewhere. And we're kind of well past the point of thinking there are canals and little green men or women on Mars. We're really looking for microbial life or Earth, version 2.0. Did it evolve on Earth and Mars around the same time? 3.5, 4 billion years ago. Well, the setting was right because we've got water. Here's the very largest canyon in the solar system. We had big, huge volcanoes and lots of evidence for running water and, in fact, evidence for hydrothermal or hot water. So that's important because if we go to these places and we find nothing, and then we go to other places like where Perseverance is going and we find nothing. And I know we can't turn over every stone on Mars, but when you start looking at the habitable environments and you find nothing, which means they're uninhabited, habitable environments, then you really have to begin to question whether we are the rare Earth or the mediocre Earth. And you might wonder, well, maybe it is rare. Maybe it is hard for life to take hold. So that's really the big sort of reason behind doing this kind of work and doing these kind of searches. So here we have Spirit rover. And in 2011, Steve Ruff and a team, Steve's at Arizona State University and is a collaborator of ours now. They were driving Spirit around in Gusev Crater around in the Columbia Hills around Home Plate, which is this deposit here of ash here, 80 meters across. And here is Spirit's final resting place right here. And then the area that's dashed shown here is a very important area because they accidentally discovered opaline silica on Mars. Now, people knew there was silica from orbit, that there was silica on Mars, but this was finding it on the ground with a rover. And I'm sure most of you will know the story that the rover, one of its wheels got stuck, so they turned the rover around, drove it backwards, and it was dragging. One of the wheels was dragging as it moved. And I would, if I were in the audience right now, jump up and do an imitation of that, but I won't do that here. But there, so it drove over this red regolith, and the soil, and then gouged out by accident this white stuff. And of course, everybody stopped and went back, and the rest is kind of history. They realized, started to realize what they had. So if we look over here on the left, we see that this silica, when they looked at it with thermal emission spectroscopy on the rover, so for example, this black line, they found these different wavelengths in this pattern that really matched hot spring silica deposits, both at Yellowstone and in particular in Chile in the high Andes at El Tatio. And they realized they were looking at opal and halite, which is salt. And opal on Mars, 3.5 billion or more years old, is incredible, because on Earth, all of that stuff transforms through pressure and time into quartz. But no, on Mars, it's opal. And these features, when you start really taking a look and mapping them out around home plate, you find that they actually have a form or a shape or a texture. And that texture is knobby and digitate, which means finger-like. And so they're really strange looking. And so here you see at different scales on Mars, the digitate silica that they found with that rover. And over here in Chile, Steve and others have been doing work in the high Andes, which are really a great analog environment for Mars, because you've got hot springs, you've got volcanoes, you're at high elevation, so that is equivalent to a thin atmosphere, and you have aridity, so these springs don't pour out lots of water like at Yellowstone. And in 2016, Steve and his colleague Jack Farmer, who happened to be my mentor at NASA Ames, they found that these are actually microstromatolites. So they've got microbes silicified into these finger-like features. And so the question, of course, is, are the Martian examples stromatolites? And despite the fact that they look like stromatolites, I mentioned to you that you can have things that aren't, that are pseudomorphs, that look like but aren't stromatolites. And so that really kicked in a lot of excitement, but it also put the Spirit rover and going back to home plate and Columbia Hills on the map for the Mars 2020 mission. So where these things form in modern hot springs, if you look at a cross section, and this is all the work we've been doing, what kinds of microbes are found where, under what conditions, under what temperatures, and they're found in channels. So shallow channel deposits, you can see here at El Tatio or in New Zealand, and we're going to that spot next week. Where do they form but in shallow outflow channels and hot springs? And now if you went back to Columbia Hills, you might want to also drive around and go to Pioneer Mound, which was seen by the rover, but they never really had a chance to visit it. And so Pioneer Mound is another location that might actually be a hot spring vent. They actually found that the reddish rock that's part of the top of that mound is actually silica rich. And the other rocks, which are here in false color blue, are actually basaltic igneous rocks or volcanic rocks. So they've actually wondered, because now they know this mound is made out of silica, was it a hot spring? And here at the same scale out in Chile is an extinct hot spring mound made out of this silica known as sinter. So that's another place to explore, and you see that where they're active, you get the hot springs and the mats forming. So maybe yes. So briefly then, in 2017, when I joined the team, they had just narrowed the search for the Mars 2020 rover landing sites. I think they started with something like 24, and they ended up with 8. And then when I joined, it got down to, that year it was brought down to 3. So there was Jezero Crater, Columbia Hills, and Northeast Syrtis. You can see, where are we here? Yes, so here's the Curiosity rover over here, and here's our location, number 2, Columbia Hills. So as you well know, they were looking at other things. They ended up choosing this beautiful poster child image of a delta in a lake over here, Jezero Crater. Anybody who does geomorphology would love that and certainly want to go there, but there's also water-laid deposits, water-laid minerals, and so they're going to look for organics on the edge of the delta. And as you know, that was launched, and we have Perseverance heading to Mars right this minute. So briefly, other ways to look for life in the solar system. We can actually find meteorites from Mars, and there are annual meteorite hunts all around the world, including in Antarctica. This one here was found in 1984. ALH 84 is the year. 001 is the first one of that year. and ALH stands for Allen Hills in Antarctica. And it was in 96, they realized it was Martian in 93, and in 96 they claimed that it contained signs of past life. I was at NASA then, and I never saw my postdoc supervisor again after that. He was busy like in Washington, DC, giving testimony about going to Mars and other things because of this. But it's very controversial, and there are many things that I can't get into here, but one of the controversial aspects is that these features here in the meteorite are really tiny. They would have to be nanobacteria, 10 to the minus 9 meters. And so people wonder whether they might be pseudofossils because bacteria on Earth are much larger. And there are other reasons that this meteorite is controversial, but it got people to study for biosignatures in a very in-depth way that maybe hadn't been done before this. So it is a good idea to look at meteorites, but it was inconclusive at best, whether there was life on Mars that was trapped in a meteorite. So here we are now, 2020. There'll be the mission, and they will cache samples. So they'll drill and then throw samples on the ground somewhere. And then in 2026-ish, they'll start heading back. And anyway, by 2031, they hopefully will have a sample return mission back home. We ourselves are working on a sample return mission, but not with NASA. We're working on a sample return mission for Columbia Hills with Japan. So I'll keep you posted on that. And then human missions to Mars, well, when you read the literature, it says 2030s to 2050s. And no, that's not me, because I don't want to go to Mars. I'm happy to send a rover, but not me. I like being here. So that's what's kind of coming up. Now, I did want to spend, so that's a lot about Mars, because that's kind of what we focus on. But I wanted to just point out to you all a few things about the rest of the solar system and where else to search. And when we do that, we talk about habitable zones. And this is the solar habitable zone where you actually are relying on the luminosity, heat of the sun. And that has changed over time. So habitable zones also change over time. So you want to know whether you're too hot, too cold, or just right, or it's okay for the conditions to be harsh because life could be lurking somewhere. And in the outer solar system, that certainly is on the different moons of Jupiter and Saturn that have ice that's insulating watery oceans underneath. So you can get out beyond the warm part of the solar system if you can create heat and liquid water another way. So here we've got an artist's rendition on Europa, a moon of Jupiter. The ice on the surface is moving around because it's all cracked. We call that ice tectonics, and underneath there's water. Here's an imaginary probe that's opened the door and that driving around and finding a hydrothermal vent or some kind of vent on this moon. I know that's all made up, but there certainly is an ocean under there. And people are very, very interested in exploring the outer solar system, going back and doing more work. And then, of course, the geysers in space from Enceladus, the small little moon of Saturn. First imaged, I think, really with Hubble, but Cassini did some incredible work out there. And the idea there is that because of what they've been able to fly through this geyser and get some information about what's going on underneath, and there was silica in that material, as well as some other elements that made them think that water and rock are interacting down on the bottom of the ocean on Enceladus, and that there may be life down there. Not whales, not fish, but maybe microbes. And so a great analog for that would have to be Antarctica, where we have subglacial lakes and circulation and sediments and possibly life in these subglacial lakes. In fact, from drilling, they have found microbes down underneath some of these lakes. So that's the analog on Earth for looking for life in the outer solar system. I did want to mention Titan briefly. Very cloudy when we look at it with visible light. It's hard to really see anything on Titan because it's got this very thick atmosphere. And so it's now, we know from Cassini in the Huygens probe, we know from orbit that there are actually lakes, and shorelines, but not of rocks as we know it or water as we know it. It's too cold. But in fact, this watery area, this is false color, is methane, liquid methane and ethane. So it's methane, which is a gas on Earth. It's so cold it can actually flow like water on Titan. And when the probe was released and floated down through the atmosphere and used I can't remember how they photographed this. You guys will know, not me. But here, what I want to point out here is the shorelines that you can actually see. and rivers made out of methane. So there's shorelines and lakes and methane, and the rocks, when it landed, this is a picture from the probe, these boulders are in fact, it's water ice, but it's so hard, they're pretty much rock. So the Dragonfly mission has been approved, New Horizons, just recently. And so they're going to explore these hydrocarbon dunes. So they're sand dunes, but they're made out of hydrocarbons. And they're going to send these different probes, these quadcopters around to explore Titan. So that's a mission coming up. And of course, you've probably all heard about this idea of the dark streaks in the clouds of Venus. Could they harbor microbes? The idea behind this is that Venus was in the Goldilocks zone for the first 2 billion years of its history until everything got too hot and the sun got too hot. So are there microbes living in the clouds of Venus, green clouds, so to speak? Are they there now as a remnant from this time in the past? That's the question. And so we know that astronomers actually turned a couple of different big telescopes on Earth towards Venus and discovered phosphine in the spectrum of Venus, pH3, which on Earth is produced by life mainly, but it could be weird chemistry on Venus. And then very recently in the news, maybe they didn't measure this signature correctly. It's just one line on an absorption spectrum. So that's very new news about whether there really could be life in the clouds of Venus. Looking maybe not so good at this point. And then I can't, finish without, because I'm getting towards the end here, not quite, but I got to finish with talking about the extrasolar planets and the discovery of extrasolar planets, which was kind of in the realm of science fiction 20, 25 years ago. But now, of course, we're on the cusp of finding something that people have dreamed about for thousands of years, and that is another Earth. And there's a great history to all of that, including people being burned at the stake back in the olden days for thinking that there might be other planets out there. And now, of course, we know there's more than 4,000, and there are a much smaller number that are Earth-like. The way we search is biased toward finding Jupiter-sized planets. That's all changing with new telescopes coming online in the next few years. And this is super important because now that we know there's quite a lot of exoplanets, it means that, gosh, there's a whole lot of places in the galaxy alone, our galaxy alone, depending on how you calculate the Drake equation. You could range from somewhere like 20 planets that are like Earth and should have civilizations to in the millions. So where are all the aliens, right? Okay, well, in 2015, breakthrough initiatives came into life. Listening for sounds of extraterrestrials is one part of the breakthrough initiatives. It's Breakthrough Listen. And it was Yuri Milner, an entrepreneur who studied physics in university. He's Russian, but I know he has a big house in Los Altos Hills because I've been there. And he's now spending his money on funding the search for extraterrestrials. And one component of that is Breakthrough Listen. And so there's a lot of very famous people here. I won't go into, I don't have time to get into who they all are. But this is when they announce breakthrough initiatives. They give away prizes for all kinds of inventive things. And they're doing lots of different things. So that's given a big boost to radio telescopes in this case. And they've just finished a 3-year stint renting time on some very expensive big telescopes around the world. And so far, nothing. But they have improved vastly the search and the way to search and the way to process the search. And so they're increasing all the time their ability to scan more and more of the sky. The other thing that Breakthrough is doing is Breakthrough Starshot, where they want to go to the next star, Alpha Centauri, 4.37 light years away. And they want to send tiny little nanocrafts, teeny tiny little things, and with solar sails using a laser pulse to get them off the Earth at about 30% the speed of light. They're going to try to do this and then go over there and do something. And I guess doing something means maybe take some pictures of these exoplanets, which are in their star's habitable zone. And so I think Yuri wants to be alive for this. So he's really pushing the envelope. And there are a lot of people in the San Francisco Bay Area in particular, but other parts of the world, working on everything from the solar sail to the chip to the laser. And I don't know if they've made a lot of progress lately. I was going to go to the meeting this year, but hopefully I'll get to go see what they're up to next year. So in summary then, we've got a solar system here with a lot of celestial bodies, moons and asteroids and planets, and a lot of potential for finding signs of microbial life. We're looking for life in habitable zones, and we use what we know about extreme environments on Earth to help us narrow the search. So on that note, I will wrap up and happily take questions, and just want to say thank you very much for inviting me to present.
Right. Well, thank you very much. Then we have a lot of questions that have come in, and so we'll see if we can get to as many as we can. So maybe we could have you stop sharing your screen so we can see you. So going back to earlier, so Elizabeth was, she noted that the Spirit rover's final discovery was the silica on Mars and the possible hot springs. Are any future rovers equipped with instruments that could identify biosignatures on Mars?
That is a really exciting topic. Thank you, Elizabeth. And it's hard to answer because of this. It's because biosignatures, we've learned from that Martian meteorite that I talked about, that you do need different lines of evidence, like extraordinary claims require extraordinary evidence, as Carl Sagan said. I'm paraphrasing. And so if you just have something that looks like a microstromatolite, or even if you get an organic chemistry signature, and a lot of the rover instrumentation is around geochemistry. So it depends on what you think is a biosignature is the answer. And I have really watched from mainly afar that the geochemists think that their signatures, which are organic chemistry, so compounds with carbon, that those are better biosignatures and more robust than textural biosignatures like the ones I've been showing you. The best answer is to have both. Because you need to know the context, and you need to know, for example, how these things grow, and if they're showing life-like growth patterns, as well as them being made out of carbon. But as we well know from Curiosity, when they found the organic carbon on Mars, they really couldn't tell you where that carbon came from. And it's in some mudstone, which is fine, but that could have rained out of space. It could be exogenous, outside of, coming, not even from Mars. So what we're talking about here is looking for signals that come from Mars. And so that's really important. And so you need to actually combine all of these things. So there's a list of biosignatures, and some of the Mars instruments can characterize some of those things, and other things will have to be characterized back on Earth with return samples. And so this debate is near and dear to my heart, because people are publishing papers in the scientific literature ranking what they think are the more important biosignatures. And I sort of take issue with that, being a geologist, because it depends on what discipline you're in terms of what weight you put on a biosignature. And I think the best bet for the best science is to consider all the possible potential biosignatures and then get those samples back to Earth.
Right. No substitute to having the rocks in hand. I'm an ex-geologist myself, so it's...
So you should know. Luca, I just see a question. I'll just jump in because it's right at the top, and then please. You guys can go on. But I do see one that I can answer, and that is that Luca is the last universal common ancestor. So the ancestor from which we all came, and would have maybe never even had a fossil record. So it might be something we never even can see. But people are trying to understand, was Luca a thermophile? Did it like hot temperatures, or was it a mesophile? Did it evolve in cooler water? We know we need, on Earth, we need water for life, and we need certain elements that are in all living things. So Luca kind of would have had to have these things. It would have had to evolve or come from non-life to life, and that's Luca.
Right. And then we move on. Stephen was, in reference to Perseverance, would it have to find definitive evidence of current life on Mars, perhaps subterranean, to prove life exists elsewhere, since structures on the surface could mimic biological processes and not necessarily be a sign of life itself?
Well, you know, the Viking missions were trying to cook up with a bit of, soup, chicken soups, quote unquote. They were trying to see if the Martian soil would, give off signs of life, like gases, some kind of biogeochemistry. And the results were either, depending on who you talk to, either inconclusive or maybe not. And we now know that the surface is really harsh, right? It's got perchlorates, which destroy organic material. And of course, the atmosphere is thin. There's a lot of radiation. And so then you've got to drill, to answer Stephen. You've got to drill to get down below to find that subterranean life. And how far can we drill? Well, the ExoMars rover that ESA, European Space Agency, will be launching in a couple of years, I think. I can't remember. It's 2022, I think. And they are going to drill, but how it's not 100% certain. How far will the cosmic radiation go? Are they going to drill into anything that might be a habitable environment? I mean, we don't really know till we get there. And InSight lander, which is there to do, among other things, measure Mars quakes. I'm sure that InSight was trying to drill into the Martian regolith, and it turned out to be harder than they thought. And so if we could just send geologists there, I could tell you with a rock hammer, you'd solve all these problems in about 2 seconds. But we can't yet send geologists to Mars with a rock hammer. So we are really limited, actually, to be totally honest, with the technology that can go there and also what we can measure. So my feeling is look for signs of past life, and certain places on Mars will be good for that. And go ahead and look for, living things as well, but they will have to be sheltered from the current situation on the surface. And of course, we always have to worry about us contaminating Mars. So the whole idea of planetary protection is quite important, since we're planning to send humans there supposedly in the 2030s. How do we protect the native wildlife? I don't know.
Yeah. I think that's an interesting thing with the limitations of sending the robots to Mars, is that if we sent you could probably do in a week what the rover does in a year or more. So it's
exactly. And the other thing too, Brian, is that they're landing on all these really flat surfaces. And what do we usually do? We go to the place where the rocks, give us a window on time, which is stratigraphy. So we want to go to the very places that rovers don't go.
Yep.
But yeah, we can't do that yet. I'm sorry, I know there's questions below this one, but I'm just seeing one right up at the top. So I'll just quickly answer Kevin's question about trying to make life in test tubes since the 70s. That's true. I know there's no real success except for incremental, like being able to encapsulate something like a protocell using lipids, so fatty type molecules, or taking stuff from a meteorite that's got bits and pieces from the solar system that are the building blocks of life, and being able to create parts of protocells, things like that. There are a couple of places, there's one in the US and there's others being built, that make a Hadean atmosphere, which is the first atmosphere of the Earth, and then trying to do experiments under those atmospheric conditions. It's quite tricky though. So no, we would have heard about it by now, if anybody had actually made life in test tubes. It might be hard to make life. I wonder whether it was just certain situations or circumstances that just worked out, despite all those exoplanets out there. Maybe it is really hard to get just the right combination. Where does Enceladus get its heat to melt its ice into liquid water? Super question. Both Europa, Enceladus, and some of the other moons. It's that gravitational pull of Jupiter or Saturn. It is, and there's a huge amount of radiation coming out of those planets. So my understanding is that it's the gravitational tidal massaging, like much worse than on Earth with the moon. And that's keeping things warm under the ice. If anybody else knows anything more, go ahead and add to that. So you can help me out.
Yeah, well, we can go to the next one here. So Darian says that based on what we've experienced with COVID-19, if we find life in the solar system brought back, would a virus be very likely, and how easy could it wipe out human and animal life? What precautions could be taken to prevent this, or are we lacking knowledge of how to protect ourselves? Which is actually kind of interesting. I actually wrote my most recent column for Mercury magazine, had to do with Kim Stanley Robinson wrote a book called Aurora, where they go out and there was an unknown prion that discovered that ended up killing everyone that went down there. And so this is a real, very real concern, isn't it?
It is. It's just a question, though, of whether there are those things out there. But I know it's in sci-fi, but a lot of things in sci-fi are actually possible. We just don't necessarily know how to create them. Things like warp drives and wormholes aren't just science fiction. They within the laws of physics, it's possible, but we just don't know how to create them yet. So, I'm not a virologist, but we probably are lacking knowledge of how to protect ourselves at this point. And back, when we brought astronauts back from the moon, we all know that they they were walking to their isolation chamber out in the open and things like that, or whatever they did wasn't very secure. We now know that probably the moon is no threat, but it is a great question. And I know people work on this for their careers. So we do need people to be considering this every time we go anywhere outside of Earth, even here on Earth, as we well know this year.
All right, so William wonders, why is there so much, or why does it appear that there's so much blue soil and rock on the red planet?
I'm not totally sure where that question comes from, but the photo that I did show that had blue rock was false colored to show the difference between a volcanic rock, a basalt, and the red was a more silica rock. So a lot of times we have to be a little bit careful and check those photos and make sure they're true color. We often use false color, even in my work, to delineate things like here's where the carbon is and stuff like that. But I don't know if there's real blue soil there, but I know that the photos I showed were false colored.
All right, so I know we're getting close to the end here. So let me jump down here and get kind of a little more speculative. So Gordon notes that astronomers were humbled to find that using our solar system as an analog for exosolar systems was way off base. Do you think astrobiologists will be similarly humbled when or if life is identified elsewhere in the universe?
Yes, we will. I think there's heaps. I think there's lots more that we can't even, that science can't even like there's what we can do with science, but then there's just got to be so much more that either our science hasn't got to yet, or that just somehow is outside of science that we just are not going to be able to observe. And I don't even, this is just a feeling I have. So I think we really, we are trying to imagine something, and then it's going to be something way more surprising than we ever thought. So I totally agree with you. We're going to be very surprised by all that. I'm sorry, there's somebody who asked, can you comment on your current or near future collaboration with Japan Space Agency? Okay. So we're in the, so I've not been, I was at NASA many years ago as a postdoc, and then I left and came here. So I didn't stay in NASA. So I don't work with space agencies that much, but what's happening is that Japan, there's a bunch of young engineers in Japan who get a little tired of the institutionalization of space exploration and the giant unwieldy programs that sometimes happen out of big institutions. And so I don't know if you follow what's going on with Japan, but they are really good at launching cheap and efficient and successful missions. And so there are a team of engineers over affiliated with the Japanese Space Agency who we've been interacting with mainly through Australia, New Zealand, and a few other countries over this side of the world. And we are actually pitching it's called LifeSpring. It's a mission that doesn't exist yet, but we're working on the early phases of it to go back to Columbia Hills and sample those silica deposits and bring them back to a world-class laboratory in Japan that is about to receive the samples coming from Ryugu, the asteroid that was sampled by Japan many months ago, and is about to bring its sample back to Earth. And they are postulating that it's full of organic material. And unlike the hype around the NASA mission that just sampled an asteroid, NASA wasn't the first to do it. And I know NASA has not ever said that, but the US media really likes to say it's the first time that anybody's ever sampled an asteroid like that. But Japan is amazing. The more I see, the more I learn. I am astounded by how cheap their missions are and how good they are. This little probe that's bringing the sample back to Earth from that asteroid is not even done with its mission. It's going to drop it off, send it down to us, and it's going to go back out to look at another asteroid. Oh, that's just amazing to me. So anyway, we're astounded by it. So we're hoping to work with them on an actual mission that should cost, I hope, a fraction of perhaps what's being postulated for the sample returns through NASA, I hope.
Well, I've got a few more questions, and so you can see them there. And so I'm going to let you choose what, and I know that we're at the top of the hour, and so we want to, I don't know whether you're willing to stick around and then everyone else can just kind of, take off when they feel like it, but it's up to you.
Well, I'm happy to hang around for a little while because I'll talk to one single person who might be interested in listening or okay, telling me their ideas. So if people want to disappear, and I know some of you, it's late for some of you, I'd be happy to go off just to do a few more questions if people are okay. And Brian, just stop me, please, because I don't want to overkill. I do myself personally have a meeting here in my own office in a half an hour. So I'm telling you what my window is.
Well, we'll keep it short. We'll go for a couple more here.
Okay.
And so let's go back up here to the top. So Elaine said, besides Mars, where would you suggest would be the second best place to look for microbial life here in our solar system?
Yeah, I mean, this is personal now, not necessarily the best scientifically, but I just think I'd really love to go back to one of the moons of either Saturn or Jupiter and really take a look at those geysers. And I know it's really, the ice is thick, but if there were a way to take a heat probe down right through the ice and then send out little, swimming autonomous vehicles, that's what I would do. I think it's really exciting. I don't know about yes, you can use perchlorates for rocket fuel, but that's as far as my knowledge goes. So yeah, that's okay. Let's see what else. All right. So if the search for extraterrestrial life assumes that there are civilizations that would have already evolved in past, what signs or geological or biological flags that you might look for that would be their footprints? Well, oh gosh, well, a layer of plastic maybe. I'm being a little facetious there, but yeah.
That might be about what we leave to the future here. So.
That's kind of what I'm thinking. In the sci-fi world, there are really a lot of things about that, and it's probably a bigger topic than we can really get into here. But I guess what I'd focus on is that the solar system is, the universe is 13.7 billion years old, plus or minus. And so other civilizations could have evolved and passed, absolutely. I just think everybody's so far apart from each other. It's hard for me to imagine us getting anywhere where we can see any of this. I almost feel like they really have to come to us with much more advanced technology rather than us being able to go to them. So I'm more waiting to hear from them than me going out and saying, what should I look for? And all those radio signals and nothing. It is a little discouraging, but it's also still really exciting. I mean, I'm both discouraged and excited about it at the same time, which I know is a little weird. Somebody asked about a T-shirt of my last slide, which has a bunch of microbes that have been covered by some kind of storm event and then all silicified. I'd be happy to donate that, but I want a T-shirt too. So you have to mail me one to New Zealand, and I'd be happy to give you my photo if somebody could make me a T-shirt. Thank you.
All right.
Thank you.
So I guess that, that last comment that you made, it kind of points out the difficulty of fossilizing things at all. We have a hard enough time deciphering the history of life. And then if all of a sudden we're not renewing the human presence on the Earth, and you have all the erosion taking place, how much of it is actually going to get preserved? And so, it's actually somewhat unlikely that there would be a whole lot of us left over a couple billion years from now for someone to actually find. So
yeah, the only comment I would make, because it is a really good comment, is that on Mars, as a geologist, what really blows me away is that the hydrothermal silica at home plate is opal. And opal doesn't hang around that much in the geological record here. It transforms to quartz, which is good and bad. If you've silicified something like a microbe early on, then usually it's fairly well protected. And even if it goes to quartz, quite a lot of the time it preserves relatively well. So what's really interesting to me is that the opal on Mars is still opal. And that means that there's not much of a water cycle going through. Now, the whole place could be buried under a bunch of dust right now. I don't know, but it is fascinating that those little digitate structures, Steve and others have done experiments to wind blast silica on Earth, similar silica on Earth, and they can't produce the same kind of structure. So it's not a windblown feature. So interesting, A, that it's so opal, and secondly, that it's now exposed. There's been a bit of ash that was over it and it's been eroded out, but it doesn't seem like those finger-like things could be formed just by wind blasting.
Well, one of the things that I was wondering too is if it's still opal after all this long time, and I wonder if there are some other minerals that you can kind of use as a check on the process at which. And so I'm thinking in terms of on Earth, olivine tends to kind of go to glass in basaltic rocks, and so the dominant rock type on Mars is a basaltic composition, and so presumably there's an olivine, or the olivine, maybe we don't know because we don't have a thin section of it, but are the olivines still olivines, or have they turned into something else like they would here on Earth.
Some of the oldest life here on Earth has, so there are these beautiful stromatolites that have been published recently that are made out of pyrite, which is fool's gold. So the organisms didn't make stromatolites out of fool's gold. It was replaced. And sometimes that's a good thing because then it preserves the material. And sometimes, of course, it's a bad thing because then it preserves, it destroys detail. Somebody here has actually said, what if the abundance of heavy elements has only just now in the last few billion years got high enough for advanced life with enzymes with catalytic centers based on chelated heavy elements? We might be the first. If that's the case, then we're definitely very lonely because, we got to wait around for the others. So yeah, of course that's possible. And we don't know. I mean, the thing that is incredible, as you all know, because you're all interested in astronomy, is how much we actually don't know. The more we learn, the more we find out that we don't know a lot of things. So, yeah.
So let's make this the last question. And so Spencer wants to make take the Martian opal and make a ring out of it for you.
It's not it's not precious opal though, unfortunately.
But let's make this the last question. Alan asks, how limiting are our assumptions of life on Earth, carbon-based, requiring water, defining life elsewhere in the universe?
Well, they're limiting for sure, but when you look into it in a little bit of detail, and I'm not a chemist, but I've looked into this a bit, and that is that if you want to base life on silicon, look at silicon. It's no wonder that the Earth's materials are made out of silicon and life is made out of carbon. Carbon can make so many different bonds. It can make so many different kinds of organic molecules that are so flexible. And so what I've read about things like silicon is it's just less, it sounds stereotypical to say it's more rigid because it makes rock better, but it's not as flexible for evolution of biological systems from what I understand. So you start to kind of limit yourself. And then when you look at other solvents, not water, say ammonia or methane or something like that, well, them being in the right form, being, liquid at really cold temperatures. And then when you're at so you've got methane and you're at really cold temperatures, can you have life like at minus 150 or something? Well, then catalytical processes go really slowly. So then you're stuck with that. And so everywhere you turn, you end up back with carbon-based life and water. So that's what I've seen in my studies this year on astrobiology as I've been learning about it while I've been teaching it, is that it's hard to come up with other materials that aren't as awesome as what we've got here. And of course, we are in the habitable window of liquid water. So it just seems pretty fortuitous that we happen to have everything all lined up just right. That's why I wonder whether maybe we're a rare Earth.
All right. Well, thank you so much. That's all for tonight. Thank you, Kathy, for joining us this evening. And thank you, everyone, for tuning in and hanging in there for a little bit longer here. So you'll be able to find this webinar along with many others on the Night Sky Network's website in the Outreach Resources section. You can also find it on the Night Sky Network YouTube channel. Each webinar's page also features additional resources and activities. And so it's already up there, but we will refresh things probably tomorrow so that we'll update at least the Night Sky Network website. Join us for our next webinar on November 17th when Carl Hergenrother from the University of Arizona's Lunar and Planetary Laboratory will bring us up to date with the OSIRIS-REx mission to asteroid Bennu. And they have the excitement from last week of actually grabbing several ounces, I think, of material. So keep looking up and we'll see you next month. So thank you so much, Kathy. And this is fantastic. And thank you for hanging in there for another 10 minutes or so to get the questions. And we never really let Daniela introduce herself to the group, but